This is the Exponential Growth and Decay Day 1 Notes video. In this video, we are going to talk about exponential growth and decay in the context of a question, and then also dig a little bit deeper with how percent growth and decay look inside each of these exponential functions. So the first thing that I wanted to address is that we are and have talked about exponential growth. So exponential growth means that we're multiplying something over time. And when we do that, you are going to see a graph that increases at a curve from left to right. Exponential decay does the opposite of that. It's going to go down from left to right. And in an equation, you will find that the initial value is going to be multiplied by a number that is bigger than 1 over and over and over again with exponential growth. And in exponential decay, that initial value is going to have a multiplier that is smaller than 1 that multiplies by that initial value over and over and over again. Now, the first thing that I want to discuss with everyone is that when we are dealing with percent growth and decay, we often are going to see things that say an interest rate of 10% or exponential growth of 3% or exponential decay of 5.5%. And in order to be able to use those percents in our equations, we have to be able to write them as decimals, because you can't use an equation and just write like 5% in there. That's not how math works. We have to convert it into a number that works well with algebra. So the directions say write the multiplier you would use for exponential growth and decay down below here. So when we are dealing with percents, it is always best to compare to 100%. When we are dealing with exponential growth, when there's an increase, we will add. And when we are dealing with a decrease, we will be subtracting. So a 12% increase, we'll start with our 100% each time. And because we're dealing with growth, that would be 12% or plus 12%. Which is going to equal 112%, but in the equation, we would need to write this percent as a decimal. And in order to do that, we write it as moving the decimal place 2 spaces to the left would give us 1.12. And the reason why we move it 2 spaces to the left is because percent means per 100. 100 has 2 decimal places. We're really dividing that number by 100. So 112 divided by 100 is 1.12. That's where that comes from. We can see this with a couple other examples. Again, if it's 40% growth, we're just adding 100 plus 40%. So to us, that looks like 140%. Which is the same as a multiplier of 1.4. So what I have in red is what we would use in the equation. We can also, and this is where some people are like, what, there's like a decimal in a percent? Sure, we can have decimals in percent, 7.5%. So 100 plus 7.5% is 107.5%. Move the decimal place over 2 spaces to the left, per 100, 1.075 is what we would have to use if we had to create an equation. So let's do the same thing, but now look at decrease or decay. We still start with 100% because we're comparing to 100, but in this case, we'll take away the 12%. So we end up getting 88%, which as a decimal, we move our decimal place 2 spaces to the left. What we would write in the equation is 0.88. We could do the same thing with 40% decay. 100% minus 40% is 60%. And if we move the decimal place over 2 spaces to the left, we get 0.6 or 0.60. They mean the same thing to me. Again, we can do the same thing with decimals. 100% minus 7.5% is equal to 92.5%. If you didn't know that, you could use your calculator. And that becomes 0.925. So let's just take what we did up here and see how it would look in action when we have a word problem. So example number 1 says that there is $4,400 placed into account initially and has an annual interest rate of 8%. says in the first box to write an equation that models the value of an account v of t after t years. Well, exponential functions are very similar to linear functions that are in y equals mx plus b form, only we don't have a plus, we now have a multiplier. So our y value in this case is v of t. The value of the account is equal to $4,400, right? But something is happening over time. It's growing. An interest rate means that we're gaining money. Yay, we like when this happens. So we're going to multiply that $4,400 by this multiplier every single t years. We could show this number, which we don't have yet, and multiply it and multiply it and multiply it and multiply it, or we can just write to the t power because exponents are repeated multiplication. So we now need to figure out, what do we put in here? Can we just put the 8% in here? Well, no, that's why we just talked about all of this math love that we gave these numbers ahead of time. We're dealing with 8% increase. So this is 100% plus 8%, which is going to give us 108%. But in order to get this in a decimal format that's usable in our equation, we're going to write 1.08. Okay, now this next question that some of us might focus on in class and others might not, depending on where we're at in the topics, is we're going to interpret this. But please know that you will also see this on day 2 if you don't get to it in day 1. But how much will be in the account after 10 years? So right now we want to hear about years. We're looking at the time. They said 10 years. So the thing that we're going to do is we're going to take our equation and we're finding v of 10. We're finding what the value of the account is going to be, that's a 4, after 10 years. We're going to need our calculator to help us calculate this. When we type it in, we end up getting 9499. Well, this says to the nearest cent, which means that we just want to round to the hundredths place value. So this would be 0.27 because we round that 6 up because it's next to a 9. Okay, let's look at the second example. So example number 2 says a population of 20,000 geese is leaving New York at a rate of 19% per month. So if you're thinking what I'm thinking, it's going to ask us to write an equation. It tells us what the y value is. It tells us what the x value is. So y is equal to the starting number of geese. And what's happening to these geese every year? Well, we're losing them at a rate of 19%, so we have to figure out what that multiplier actually is every single month. So how do we get it? Well, that's going to be 100 minus 19%, which ends up giving us 81%. But in our equation, we have to write that as 0.81. Now it wants us to figure out how many geese will remain after a full year. Well, how many months are in a year? That would be 12. So we want P of 12 is equal to 20,000 all times 0.81 to the 12th power. Head over to our calculator to find, well, we don't want parts of geese, right? So this is approximately 1,595 geese. Something that I just want to say in closing is that when we are dealing with percent increase, it is much easier to see that percent increase with our multiplier than it is our percent decrease. And what I mean by that is, oops, I didn't mean to erase that. So what I mean by that is, if you see 12% in a percent increase, you see the 12, right? The 40, you see the 0.4 40, the 7.5, you see that as 1.075 in the growth. But that is not the case when you're dealing with exponential decay. So just be careful when you are thinking about exponential decay. I'm trying to highlight it, but my computer's not letting me. Just know that decrease and exponential decay, you're not always going to see that multiplier very easily.